the relatively new work. I have the archive number here, and some recent results since then. What's the main question? The conformal window beyond QCD. We know, oh, I don't see my slides, I'm sorry. We know that if you take NC colors with NF flavors, and here I consider fundamental flavors, but anything else would work, we know how the beta function behaves. We know the beta function even up to 5 loops in the MS bar scheme. I wrote down the first 2 coefficients. For small number of flavors, that's QCD, the beta function is negative, asymptotically free, confining. We are all familiar with that. We increase the number of flavors at a critical number n star, the beta function will develop a second 0. At 2-loop level, it happens when the 2-loop coefficient becomes 0, which happens for fundamental flavors around 8. But of course, that's a non-perturbative question. We don't really trust that. But that is where conformality sets in. And if we increase the number of flavors beyond a certain number where the 1-loop coefficient becomes positive, then we lose asymptotic freedom, we get into the infrared free regime. So these are the 3 possible phases of gauge fermion systems. I am mostly interested in the one in between, the conformal regime. The interesting thing to note here that perturbatively, the conformal fixed point, this infrared fixed point, emerges at infinitely strong coupling. And then as NF increases, so at n star, the coupling is at infinite. As NF increases, it will move in until it merges with the Gaussian fixed point, and then we lose asymptotic freedom. The system becomes infrared free. That's the perturbative picture. Few people believe or that it's possible that that's what will happen, but not necessary. There is another scenario that has been discussed for the last 15 years or so, maybe 13. The idea is that the conformality emerges as the beta function kind of develops a hump. Right here, that is, we can parameterize the beta function as some constant times G minus G star squared, where this G star is where the beta function will develop as 0. The alpha is a parameter that, for example, the number of flavors are related to the number of flavors. And as alpha becomes critical, the beta function will have a 0 that just touches the x-axis. That's the opening of the conformal window. I got this plot, these 2 plots actually from the Kaplan et al. Paper where I first saw this possibility or hypothesis, but there are several other papers since then. Now, if this is the picture, this is very interesting because it says that conformality is lost when 2 fixed points, which are denoted here by G minus and G plus, merges, moves together, and the corresponding critical behavior is more like Kosterlitz-Thales, BKT-like scaling, not the usual scaling behavior. If this is indeed the case, we could look for numerical signs for that. For example, we would expect a continuous phase transition both at the second ultraviolet fixed point and at G star. And we would expect some kind of BKT type scaling at G star itself. So the question, can we see that on the lattice? Is that indeed realized? I have to emphasize this is just a possible theoretical picture. We don't know if that's what happens. If, on the other hand, if that is what happens at G star, there got to be a new emergent relevant operator. So it's useful to look at the entire picture with an extended parameter space. And this is my extended parameter space phase diagram. There at the horizontal axis is the original gauge fermion system. That's what we simulate on the lattice. The vertical axis is the new emergent operator, and most people believe it will be some kind of 4-fermion interaction. So I denote it by the coupling by capital G, and will refer to it as an NGL, Nabu-Jonah-Lazimio type model. We really don't know, but that's a working hypothesis. In that case, the phase diagram will have a real chiral symmetry breaking phase transition. This black line is a second order phase transition. The idea that a UV fixed point emerges on that phase transition when it's connected to the Gaussian fixed point of our gauge fermion system, the infrared fixed point that we talk about in terms of the beta function sits on that red connecting renormalized trajectory. So this is the setup in conformality. The question that what happens if I continue this black line here, will it hit my vertical axis, and will this green dot correspond to a second order phase transition? That is, am I going to see the effect of this UV fixed point if exists? An even more interesting question is what happens if I approach the conformal sail, that is, go back to this picture where the beta function just touches, but that corresponds to the UV and IR fixed points to merge, like in this second diagram right here. That is the picture that would correspond to the opening of the conformal window or the conformal sail, and that's where we might expect a BKT type scaling. So this is my theoretical setup, and I want to see if any of that might be observable in lattice simulations. What is the simulation? This would be a good time to have an outline. I say it is also a summary in case I lose everyone or I ran out of time. I can tell you what is coming next. What I study is two species of staggered fermions. For lattice practitioners, that is 8 fundamental flavors. I don't quite think that it is a correct description here, and I will tell you why. Basically, because 8 fundamental flavors, 2 staggered flavors will describe 8 fundamental direct flavors only at the Gaussian fixed point. And if I am not at the Gaussian fixed point because I think about fixed point merger, that picture might break down. Nevertheless, this is the lattice setup. Also, in the chiral limit, 2 staggered flavors are free of Toft anomaly or any anomalies. There is in fact, a gravitational anomaly in this system, but with 2 staggered flavors, the system is anomaly free, and it could allow symmetric mass generation, a very interesting and exciting possibility. I will touch on that later. You might say that 8 flavor has been studied to death in the last 10 years, and it's true. So why is it that I see something different than what was seen before? The reason is that every study with 8 flavors showed a very first, or at least a strong or weak first order bulk phase transition that predicted simulations to go to strong coupling. I have a suggestion of how to improve the lattice action to avoid that first order phase transition, basically by adding heavy Pauli-Villars regulator bosons. By adding those fields, I can get rid of, at least apparently rid of, this first order phase transition, go to much stronger coupling and see what happens there. And what I will show is that I observe 2 distinct phases, a conformal phase and what looks like a symmetric mass generation phase that I mentioned about here. And the phase transition between those 2 phases appears to be very continuous, very smooth. To really check if it is a first order, weakly first order, or indeed a second order continuous phase transition, I use finite size scaling. In the finite size scaling, I consider the gradient flow coupling, which I believe is new. I haven't seen that used in finite size scaling studies before. And what I see is that the phase transition indeed seems to be consistent. It seems to be continuous. It is consistent with a BKT type of scaling, which would suggest the merging fixed points. it is inconsistent with first order, and it's also inconsistent to a somewhat lesser level with the second order transition. Then one can ask that what is this strong coupling symmetric mass generation phase? What triggers that? Typically in condensed matter system, that system is topological. It is triggered by surface topology. I cannot quite show that that is the case here, but I can show that there is topology involved in generating that phase. So at least at that point, I fit into this workshop. It is a gauge system with topology, unusual topology, and unusual phases. So this is a bit of a short summary. I will show the why two staggered flavors are interesting. I will talk a little bit about symmetric mass generation. I will discuss this Pauli-Villars, which might be useful well beyond of what I am doing here, and then the finite cell scaling. Good. So staggered fermions. We all know that. I think everyone, or most everyone here, is a lattice practitioner. Staggered fermions are, even though we think about them as describing 4 fundamental flavors, they are very geometric. They are distributed in a 2⁴ hypercube, and strictly speaking, they are equivalent to Kähler-Dirac fermions. I didn't know that, but already in 1982, there were a series of papers that discuss that connection. If I take one set of staggered fermions that corresponds to 4 Dirac flavors in flat space at the 0 coupling, if I take 2 sets of massless staggered fermions, that is 2 sets of 4 Dirac flavors or 4 sets of regular staggered or equivalently 16 wild fermions or Majorana fermions. And it turns out that with staggered flavors, there is a very special gravitational type of anomaly that turns into a Z4 gauge anomaly on the lattice. And that anomaly is cancelled when we have at least 2 sets, no, when we have the multiple of 2 sets of staggered fermions. So when I take 2 sets of staggered fermions, or colloquially 8 fundamental flavors, that system is anomaly free, and Simon Ketterer and collaborators already discussed that that system is actually perfect for symmetric mass generation, that is generating mass without chiral symmetry breaking. But we'll see what if that system indeed does that. Good. Again, 8 flavor has been studied to death. How come that we still don't know if it is conformal or not, or the window? Again, the issue is that first order phase transition that every simulation runs into. I have a couple of pictures here showing, maybe let's just look at this one. A relatively large study that tried to find, assuming that the 8 flavor is below the conformal window, they were trying to find the finite temperature phase transition in the chiral limit. And they absolutely failed even on NT24. That is a huge NT, and even with 24 time slices, the phase transition didn't hit the chiral limit. It ran into this first order warp transition. So really, we don't know. There is no numerical evidence that 8 flavor is below the conformal window, or if it's above the conformal window. But the best example is that you would have to go, there was an estimate that one would have to go to n-tau 64 or so to maybe see the chiral phase transition. But that also implies that maybe there is no chiral finite temperature phase transition there. Good. So let's look at it. Pauli-Villars bosons. Why is it so difficult to study 8 flavors? Or why is it so difficult to study many number of flavors? The issue is that fermions, when we add fermions to the gauge system, they induce an effective gauge coupling. And that effective gauge coupling is a positive gauge coupling that forces the simulations to choose the bare gauge coupling, which is the plaquette term or the semantic term, forces it to strong coupling. And at that strong coupling, the UV fluctuations become huge. Anyone who has done many flavor system or smeared system or any kind of fermionic system is quite aware of that you have to go to stronger bare gauge coupling, you have a smaller plaquette, larger UV fluctuations, just due to the fermions. We have seen evidence that the first order bulk transition that many of these systems exhibit is due to these UV fluctuations. It's not physics, it is direct consequence of lattice artifacts. And that's what an improved action could have. How? Well, if fermions induce an effective gauge coupling that pushes the bare coupling to strong, then let's add to this system Pauli-Villar's bosons. That is the opposite statistics than the fermions, then the Pauli-Villar's bosons will push the gauge coupling the other direction. If I take the Pauli-Villar's bosons like we do it in continuum regularization with heavy mass, they are just regulators. They don't change the physics. They don't change the infrared physics. In fact, we can integrate out the heavy bosons. All we get is some kind of effective gauge action. The leading term is just a plaquette, and then there are, of course, higher order terms. They all go with 1/2 times the Pauli-Villar's mass. So if the Pauli-Villar's mass is order 1, this is a small term, all the other couplings are suppressed. This is an improvement on the gauge action. But because the induced gauge action comes with a negative sign as opposed to positive for the fermions, that counters the effects of the fermions. So that is the idea between Pauli-Villar's bosons. I think it's a very generic improvement. We have a paper last year where we looked at PV bosons with 12 flavors. I will show you results with 8. And I know that it helps with 4 and fewer number of flavors. It is just a good improvement of the gauge action. So what I will show you, these are just a summary slide of what you will see. I will show results with no Pauli-Villar's bosons, just for comparison. You will see that the critical coupling there is around 4.6 in whatever units, doesn't matter, it's a funky action. I will show results with 8 Pauli-Villar's fields per fermions with mass 0.75, so it's pretty much cutoff level mass. There, the critical coupling is 8.8. It's a huge difference. And I also show some results with 4 Pauli-Villar's fields, but smaller mass 0.5. There, the critical coupling is 8.1, so in between those two. An important note, all simulations that I will show will be in the chiral limit. It is possible in the conformal phase, and it's also possible in the symmetric mass generation phase, because there are no pions, no chiral symmetry breaking here. And I will use the gradient flow observable, which we all know and love. Gradient flow, as Luscher suggested it 10 years ago, T squared times E is an operator that has no anomalous dimensions, so it can be used as a coupling. It basically measures how the renormalization group flows along the renormalized trajectory. So that is the setup. And for the phase structure, here is the first picture of the plaquette. What happens to the plaquette if I go from 0 to 8 PV fields? So no Pauli-Villar's regulators. You have to trust me at this point that there is a phase transition somewhere in the middle of this plot. The plaquette does not show it. It's a very weakly first order transition. It looks rather smooth, but the phase transition occurs somewhere around 4.5 or plaquette value 1 out of 3. That's a rough plaquette. If I add 8 Pauli-Villar's fields, the phase transition moves to about 8.6 and the plaquette is above 1.7. That is enough to get rid of the most offending UV fluctuations. And with 4 PV fields, it's almost the same, a little bit smaller. So that's how Pauli-Villar's fields helps immediately in the UV fluctuations. Nobody's complaining, but why do I think that the plaquette is related to UV fluctuations? Well, that's the smallest object I can look at. That is the quantity that measures easiest how large the UV fluctuations are on this system. So it's not as theoretically well-established statement, but I think a pretty good statement that the smaller the plaquette, the worse you are on the lattice. Good. So what happens? I promise that there is topology in here. This is the topological susceptibility in these systems. And here I show only the 0 PV and 8 PV. The 4 PV is pretty much the same. Remember, these are all simulations in the chiral limit. There should be no topology whatsoever. In QCD or in the conformal system, topology is suppressed by M, the fermion mass to a par. So if the fermion mass is 0, there better be no topology. And indeed, there is no topology in the decoupling regime. And then something happens around 4.5 here, and the topology shoots up to the sky. There is a new vacuum forming here, where the standard argument that instantons create a 0 mode in the Dirac operator and that it suppresses configurations with non-zero topology fails. So I believe this implies that that is a topology-driven, or at least topology-related phase transition. The same is true both for the 0 PV and the 8 PV. They both have this phase, and in both cases, the topological susceptibility is quite dominant. In the 8 PV field, one might even argue that it shows scaling, which is related to the fact that the 8 PV phase transition looks to be second order. Good. I don't know what else to do with the topology, but I know there are experts here, so I would like to hear their opinion, and maybe we can discuss that later. The quantity I am looking at is the gradient flow coupling. Gradient flow coupling fixed, the flow time fixed to the lattice volume, and that allows me to use this coupling in a standard finite size scaling analysis. This is not finite size scaling yet. Here I just show different volumes with this ratio C set to 0.7. Of course, I have everything from 0 to 1. I just picked 0.7 here. You see how different volumes change. You might even see here, maybe in this blue line, that there is a first order transition there. There indeed is a discontinuity. While if I go to 8 PV, everything looks smooth. There is no obvious first order transition. How can I really tell if it's first order or not? I will do finite size scaling. Finite size scaling, we assume some kind of scaling behavior for the correlation lengths. In a second order transition, it is just beta minus beta C to a power of minus nu. In a BKT transition, it is an exponential form. That's the Kosterlitz-Thalès transition, e to the psi beta minus beta C to an exponent nu. These two exponents, of course, are not the same. The Kaplan scenario that I showed on the very first slide corresponds to nu equals 1. So these are the two scaling behaviors, and if I put it together, I expect that the gradient flow coupling G squared will be a universal functional form of volume times beta minus beta star to the power of nu, or volume times this exponential factor e to the minus psi beta minus beta star. So I can take my data, ask that what nu and beta star, or nu beta star and zeta, will make a curve collapse. That's an absolute standard curve collapse fit that people do in statistical systems for finite size scaling. Good. So here is an example. This is a sanity check, no PV. I have seen first order phase transition discontinuity. I expect a first order kind of scaling, which is like the second order, but with exponent 1 over d. That's the discontinuity exponent, 1 over d 0.25. What you see here is that's a fit, and the fit predicts 0.27 with an error of, let's say, 1, with a pretty good chi-square, and you can just see the data points lining up there. That's a good curve collapse fit for, I use volume 10 to 16, and the 8, which are the open squares, are not in the fit, they are just there to check. If they would be totally off, I would know that something is not quite right. So I do this fit form. I find a good chi-square and a scaling exponent that is pretty consistent with 1 over 4. So that's a first order phase transition. Certainly I can change C, this exponent will change a little bit. So this is only statistical error. Systematically, I would say it is about 0.25 with an error of 1 or maybe 2 in the last digit. That just shows that the method works. What happens if I take the 8 PV system? Same setup, second order kind of fit. Okay, nu is 0.5. That's not first order. That could be a second order exponent. The chi-square is not bad. It's a bit worse. But there is one problem here, that I cut off most of the data points. This guy suggests a critical point around 8.6 or below, and I didn't use those data points. If I add those data points to the fit, which is at the bottom panel, chi-square shoots up to 15. This is simply a not acceptable fit. That the exponent mu says that it is, if anything, this is continuous second order scaling. A 0.5, 0.6 could be even a mean field or Ising-kind scaling, but the chi-square says that this is not consistent. And that's exactly what I see with the other 8 PV action. So what happens if I do BKT scaling? In BKT scaling, I fix the exponent to 1, mainly because I can't fit 3 exponents at the same time. The data is not good enough. And I was told that 1/2, which is the 2-dimensional XY model, is 2-dimensional. In 4-dimension, the Kaplan scenario, Richkov scenario, all suggest mu equals 1. So let's concentrate on mu equals 1. Absolutely perfect chi-square. All the data points that I could not take into account in the previous slide are included. I can even take L equals 10, the smallest volume in here, and it fits the picture. And I get, I don't have the value here. There are 2 fit parameters, beta critical and that exponent zeta. Neither of them are universal. So I can show it to you, but they are irrelevant. It's not, they are not universal, depend on direction. But we see both with 8 flavors and 8 PV and 4 PV, BKT scaling has a very good chi-square, a visually very good looking curve collapse fit. This set of data prefers a Kosterlitz-Thales type continuous phase transition.
How do you determine the chi-square?
So that is the details of how I do the curve collapse fit. And I follow a suggestion that was developed for statistical systems. I basically, I can tell you the details, but at the end of the day, I imagine that I take all these points, I put a smooth curve over them, some kind of smooth cubic spline, and then I determine the difference from that curve. So this is an absolutely statistical error. There is no systematics in it. And it assumes that I have a decent curve collapse, but if the curve collapse is not decent, chi-square is huge. I can describe the details. Mm-hmm. Again, curve collapse is an art. I spent a fair amount of time learning the art, and I probably not the best at it. There are many other ways to do it much better, and I am certainly open to it. But if nothing else, when I go back to this guy and I have a chi-square of 15 that came from exactly the same kind of curve collapse than the chi-square of 1 or 2 in this case. So if nothing else, there is a consistency check between the different setup. Okay, so this is just to show that I can do different C's, different volumes, everybody is consistent, there is a drift. At small c, I don't expect consistent results because small c is just not long enough to get to the renormalized trajectory. Flow time is not long enough, or the RG step is not long enough. But once I get to somewhere around 0.5 or above, again, these are statistical errors. The systematical errors are pretty much what you see the scatter on this plot. And here, this shows what happens to the critical coupling. Again, it drifts a little bit and then settles. The critical coupling, of course, is different for the 8 PV versus the 4 PV. The exponent zeta, while it doesn't have to be the same, it turns it looks quite to be the same for the two actions. Zeta is not universal, at least not to my understanding. Good. So what? That's weird. What have we learned so far? So there is a phase transition. If I add sufficient number of Pauli-Villars fields, the phase transition gets smoother and turns out or looks very smooth, at least visually, in the sense that the plaquette or any other observables do not show two-state signal. Then I use finite size scaling argument or scaling test. I see that the scaling is inconsistent with first order. It is also inconsistent with second order, although somewhat better than with first order, because the first order has a given exponent, 1/4. The scaling looks BKT-like or working scaling. And here I have to say, when I first put that paper on the archive, I discussed with Slava Lichkov, and he really berated me to calling it BKT scaling. He said that it is working scaling, has nothing to do with BKT. So we all know BKT, but it is working scaling according to him. Good. What happened here? Good. So the question is that if there is indeed a phase transition, what can we say about the phase on the other side of the phase transition? And recall that now it is actually interesting. If I have a second order phase transition, I can define a continuum field theory. I can define a continuum limit there. So it is important to understand what kind of continuum limit do I get. And what it seems, it's not the first time we look at this phase. In fact, in 2012, with my student and postdoc, we looked at it with 12 flavors. That is what we called at that time S4 phase, because it has a funky symmetry breaking pattern. But at this point, I keep the name S4, but what I can say about the phase is it's confining. And we already know it is confining just by looking at the gradient flow coupling. Gradient flow coupling is tiny, tiny in the V coupling regime and then shoots up in that phase. That is a typical sign what we see in QCD from conformal to chirally broken. It looks to be chirally symmetric. I will show some data for that. It is gapped. That is, it has a finite mass even without developing chiral symmetry breaking, and it seems to be topological. So in the next 5 minutes that I have, I will show you a couple of preliminary plots on the spectrum, but I want to have one slice of really what do we mean on spectrum. These are staggered fermions. So staggered fermions have many pion states that we call pions. Here I look at 4 of those pion states that if you have done staggered fermions, you know what these are. They are characterized by the spin and the taste. So I have 2 states that are mainly pseudoscalar, 2 states that are mainly scalar, but they all couple to the same set of systems. And just for fun, I wrote down the definition in terms of the single component staggered fields. So one of them is just Q bar Q. The other is Q by Q with a phase factor. And then the other 2 is a Q by UQ. So I have one wing separated field with a phase factor and without a phase factor. These are standard definitions. Why do I say chirally symmetric? So chirally symmetric or axial symmetry conserved means that the scalar and pseudoscalar better be degenerate. They are better than degenerate. These are correlators, not the masses, the correlators themselves. The blue point is what we would call a pion correlator. The yellow, which is sitting right on top of it, is the scalar correlator. They are identical to about 10 to the minus 3 or 4, the correlators themselves. And then if I take what we call the gamma I, gamma 5 or T2 pion, and the S2, gamma 5, gamma I, gamma J, and other pion and scalar, Those two are also degenerate, but not degenerate with the Goldstone pion. So that shows that there is a symmetry breaking there. For comparison, this is the plot of at a beta value, which is in the conformal phase. So in the conformal phase, all four of those correlators are very, very close. There is a little bit of breaking, that's the phase breaking in that system. Of course, these are all zero mass, so it is just that the usual phase breaking. We see that in the S4 phase, we have a new kind of symmetry breaking, but it's not a chiral breaking. Axial symmetry is conserved. And if I look at the masses, so take these correlators, try to extract the mass, try to do some kind of vary the mass or the volume. This is in the S4 phase. I have data with 16 cube and 24 cube volumes. And these are these pion masses just as before. So 2 pion, 2 scalar, the A0, corresponding A0. Look at them down here. There is basically no dependence on the fermion mass. This mass is not related to the fermion mass, and it's finite, it's large. It's not going to zero, it's pretty much constant. And in the last 4 data points or 2 mass values, I have both 16 and 24 volumes. There is no volume dependence either. So this is not because there is a finite volume squeezing in here. In contrast, this guy is most likely in the conformal phase, and there 16 cube and 24 cube are very different. That just shows that there the mass is coming from finite volume scaling. So there is no issue with the volume here. This is really a mass independent generation for the hadrons that is not related to chiral symmetry breaking, does not require Goldstone bosons. This is what we call symmetric mass generation. And Massimo is going to show me 2 minutes. So I am just recapping now. This is the topology I showed that before. I wish to understand how I can such a large topological charge. The zero mass simulations, my best bet is that the instantons condense, and they condense not in pairs, because then the net topological charge would be 0, but they really condense independent of their charge. Maybe they condense on the surface, which is what one would expect from condensed matter physics, but I don't know. I would love to understand that in the future. And then really it's my summary, so I am done in time. So what did we do? I used an action with 2 sets of staggered fermions. And while I will say it is 8 fundamental flavors, I would like to emphasize that it's not necessarily the 8 fundamental flavors of QCD. There is a continuous phase transition in that system when the action is improved. PV bosons are not the only way to improve it, but it's a good one and relatively quick one to go to smooth smooth configurations. I didn't emphasize it, but if you look at the value of the gauge coupling G squared at the transition point, it is much stronger with the PV field than what was allowed without the PV. So indeed, what happens that without PV fields, the system tries to get stronger and stronger and then hits a first order transition due to fluctuations. If I add PV, I can go stronger and stronger and even stronger until I have a continuous transition. So it is a consistent picture. Finite size scaling suggests a working scaling transition, a DKT kind of transitions and transition. And then we have this strong coupling S4 phase that has every property that one would expect for a symmetric mass generation phase. And if the phase transition is continuous, that is indeed that one can define a continuum field theory on that fixed point. Now, if all these are correct, and I say all these are correct because it is a relatively new work and I wish somebody would go and check it or try to do it differently. I don't have a 5 sigma deviation or 5 sigma check because it's only me. So I control myself, but what? But if it is correct, and at this point I don't see anything scary or inconsistent in that, then that would imply that NF8 or two staggered fermions is actually the seal of the conformal window. What are the chances for that? We always saw that the conformal window will open up somewhere at a non-integer number of flavors. So what happens? What triggers it at NF8? If it is indeed the seal of the conformal window, I am 100% sure it has a symmetry driving it. It is not an accident. And what could that symmetry be? Most likely the anomaly cancellation that I mentioned, that I learned from Simon Catterall, that happens with two sets of staggered fermions. So there is a really theoretical question here that I don't know the answer, but I have a hunch that it is a theoretically well established. It has to be a theoretical issue with that. One question that, is this specific now to staggered? What would happen if I took domain Wolf fermions? Domain Wolf fermions with 8 flavors. Now, if 8 flavor or 2 staggered fermions just had an ordinary second order phase transition, I would say that domain Wolf doesn't have to follow it. But if it is the seal of the conformal window, then you cannot separate it from the Gaussian fixed point. And at that point, it doesn't matter whether I use domain Wolf or staggered. So if this is indeed the seal of the conformal window, domain Wolf fermions better show the same. Why don't we know that? Because domain Wolf fermions have the same issue as staggered. It runs into a first order transition. It can be improved by Pauli-Villars bosons, but it has to be done, and it has not been done yet. But I think it's a very interesting open question. And then I just throw out the last line in here. If indeed we have a new phase transition, a new phase, a new continuum, second order phase transition, could that introduce a new paradigm for BSM beyond standard model kind of systems? It's not composite fix, it's something else, but nothing ever happens by an accident. So I will stop here. There are a lot of questions here. I would love to hear opinions, questions, comments.